Hi students, good evening to one and all. This is something like a revision session, okay, for 10th standard maths. And so many students asked me some doubts regarding this alternate segment theorem. They wanted me to teach them again this alternate segment theorem. Most of the students, they feel it's very difficult. And so many students, they called me and they asked me to explain this theorem again. Okay. Let me try to explain you this theorem. Okay. You please listen. Alternate segment theorem. Consider a circle and a tangent to the circle. Okay. Let the point of contact be A here. I take this is S and this one is T. So SAT is a tangent to the circle at the point A. From the point of contact of a tangent, I draw a chord. This is chord AP. Chord AP. When I draw a chord to the circle, this chord separates the circle into two segments. And this part is a minor segment and this one is a major segment. This one all of you know. Okay. And this theorem says the angle made by this chord with the tangent, or the angles between the chord and tangent are respectively equal to the corresponding angles in the alternate segments. I'll tell you what are the corresponding angles in the alternate segments. Now, first let me tell you what are the angles formed here when we draw a chord and a tangent. What are the angles made by this chord with this tangent? We can say that this is PAT, one angle, and the other angle is PAS. PAT. Other one is angle PAS. These are the two angles formed by this chord with the tangent. And then in this major segment, I take one point here. At that point be some R. I join this point with that P and this A. Let the center of the circle be here, center of the circle, or let this be O. And then here at first we took a point in the major segment R and then we joined with the chord, these two points, ER and AR. Now I take another point in the minor segment. Let me name it as Q. Join this PQ and AQ. Okay. Now at first we saw the angles made by the tangent and the chord, that is PAT and PAS. Now the angles made by the chord in the alternate segments. What are the angles made by this chord in the alternate segments? This chord makes an angle PRA in the major segment and angle PQA in the minor segment. And the theorem says the angle made by the chord with the tangent, or the angles between the chord and the tangent are respectively equal to the corresponding angles in the alternate segments. That is, This chord makes PAT here in this segment, and the corresponding alternate segment is here. So angle PAT must be equal to angle PRA. So to prove, we are going to prove this. First one is angle PAT is equal to angle PRA. Second one. Then another angle made by this chord with the tangent is PAS, and that PAS is equal to angle PQA. This angle is made here in the major part, and alternate segment is in the minor part, that is PQA. Okay, this one. These two things we need to prove. Now I hope that you understand the theorem. Once again, given a circle with a center O, I will draw a tangent to the circle. The point of contact of the tangent with the circle is A. From the point of contact, you draw a chord AP. And this AP subtends two angles with the tangents. What are the angles? PAT and PAS. PAT, PAS. And here, when we draw a chord, this chord separates the circle into two segments. That is, one is the minor segment, the other one is the major segment. The major segment, I take a point somewhere here R. Then I join with P and A. Minor segment, I took another point Q, joined with P and A. The same chord makes two angles in the alternate segments. What are the angles? One is PRA, other one is PQA. PRA and PQ. All these four angles are subtended by the same chord. The chord with the tangent, two angles. The chord in the alternate segments, two angles. We are proving that, going to prove that angles between the chord and tangent are respectively equal to angles in the corresponding alternate segments. PAT is equal to PRA, PAS is equal to PQ. Okay. For proving this, we have to make some construction. Draw this diameter SC. Then join this PC. Draw this diameter SC and join PC. This is the construction given. Construction part you can show by these dotted segments here. Okay. Construction part you have to write and show. Then coming to this proof part. Proof. First part, let's try to prove the first part. First part, here you see. This is a diameter, therefore this is a semicircle. This one is a semicircle. And all of us know that angle in a semicircle is 90 degrees. So we can say angle APC is equal to 90 degrees. Angle APC is equal to 90 degrees. Reason we give angle in a semicircle. Angle in a semicircle. So this happens to be a triangle. APC is a triangle, and one of the angles is a right angle, and so the sum of the other two must be 90 degrees, because angle sum property of a triangle says that sum of the three angles in the triangle is 180. So sum of the remaining two angles must be 90. That is angle ACP plus angle PAC is equal to 90. Let's keep this as 1. ACP plus PAC is equal to 90. And then angle between the diameter and the tangent at the point of contact is also 90. So I can say angle CAT is also 90. CAT, angle between the diameter and the tangent, the point of contact, is always a right angle. The CAT can be separated like this, that is CAP and PAT. CAP plus PAT is equal to 90. I think this is 2. Because sum of these two is 90 and this 2 is also 90. From 1 and 2 we have this. What is that? Angle ACP plus angle PAC is equal to angle CAP plus angle PAT. We know that this PAC, or CAP, these two are equal. So the common angles we can cancel. And so we get angle ACP is equal to angle PAT. ACP, where is ACP? ACP is equal to PAT. But another thing is, this ACP is equal to ARP. What's the reason? Right here. But angle ACP is equal to angle PRP. ACP, ARP, because these two are, this angle ACP and ARP are angles in the same segment, the same major segment, angle made by this chord on the major segment ACP, here ARP. Both are the angles made by the same chord in the same segment, so they are equal. ACP is equal to PRP. But here we got ACP is PAT and here ACP is PRA. So from these two we can write angle PAT is equal to angle PRA. These two are equal, therefore these two are equal. PAT is equal to PRA. PAT is equal to PRA. We got this first part. PAT is equal to PRA. Now going to the second one. Okay. And here, consider this AP as a ray standing on a straight line. So AP stands on the straight line ST at A. So sum of the adjacent angles is 180 degree. So I can say PAS plus PAT is 180. And PAS plus angle PAT 180. You know this by name linear pair theorem. Linear pair. PAS plus PAT is 180. So PAS plus PAT. Just now we proved that PAT is PRA. So angle PRA 180. This one I take as equation number 3. Then the next thing. Now we know that this AQPR is a cyclic quadrilateral. All the 4 vertices are on a circle. Therefore, AQPR is a cyclic quadrilateral. I write here AQRP is a cyclic quadrilateral. So what is an important property of the cyclic quadrilateral? Opposite angles are supplementary. Sum of the opposite angles is 180. That is angle ARP. Here it is ARP this angle plus AQP this angle is equal to 180. If this is 4. In a cyclic quadrilateral, opposite angles are supplementary. So ARP plus AQP is 180. Here, PAS plus PRA is 180. ARP plus AQP is 180. So from these two, both are equal to 180 degrees, therefore we can write angle PAS plus angle PRA is equal to angle ARP plus angle AQP. This PRA is towards same, we can cancel, so we get angle PAS is equal to angle AQP. PAS is equal to AQP, that is the second part, AQP. So we can say this completes the proof. Okay, here remember some important previous facts here. That is, angle in a semicircle is a right angle. That is APC is a right angle. So that is here. And so sum of the other two angles is 90. And again, angle between the diameter and the tangent is 90. That is CAT is 90. And we split this CAT into 2. That is CAP plus PAT. 90. These two are equal to 90. So from 1 and 2, sum of these two angles is equal to sum of these two. Common angle we cancel, and so we get ACP is equal to PAD. But this another fact is, angles in the same segment of a circle are equal. That is ACP is equal to ARP, made by the same chord in the same segment. So ACP is equal to PAD, ACP is equal to PR. These two are equal, therefore these two are equal. PAD is equal to PR. That completes the first part. Then coming to the second part, here what is PAS plus PAD is equal to 180. Here we are going for the linear path theorem. That is, when a ray stands on a straight line, sum of their adjacent angles is 180. PAS, PAT, 180. But for this PAD, you can write PR. This now we proved. And then opposite angles of a cyclic quadrilateral are supplementary. That is used here. So this sum is 180. This sum is also 180. So from 3 and 4, we get this. Common angle we cancel. So we get PAS is equal to AQP. This completes the proof. Hope you have understood this. Just to go through once. You go through this problem once. Okay? Try to do on your own. Thank you.